In this presentation, we introduce damping elements. We've discussed so far spring elements, that is elastic elements, and mass elements, which have inertia. The damper represents energy dissipation in a mechanical system. Damping occurs naturally in all mechanical systems due to the energy that's lost in terms of heat with any sort of internal motion within a system. After all, systems with only elasticity and inertia would not lose any energy. Elasticity stores energy as potential energy, and inertia stores energy as kinetic energy. And so a system consisting only of spring and mass elements would continue to oscillate forever. We know there's no such thing as a perpetual motion machine, and so we know that all real systems have some amount of damping in them. In certain engineering applications, it's desirable to have a great deal of damping, and so sometimes special components are introduced to increase the damping inside a mechanical system. Now, one thing is true about all damping elements. To dissipate energy, we have to take work out of the system, and to do that, the force that's introduced by the damping element must oppose the velocity of the inertial element. It's the only way that we can actually take energy out of the system. So our damping force works to oppose the lengthening or the contracting of the damping element, but it does not respond to the actual length of the dampening element. Unlike a spring, it only acts to oppose a change. It should be pointed out that a damper decreases the energy of the entire mechanical system. It does not necessarily have to decrease the energy of any particular element in the system. So a damper can actually act to transfer energy from one element to another. Let's look at an example of an engineered damper system. At over 1,600 feet tall, Taipei 101 is currently the second tallest building in the world. But this tower was built almost directly over a major fault line in Taiwan. And in addition to the earthquake risk, the building may also be subjected to high winds from typhoons. To mitigate the possible resulting sway of the upper floors, a 730-ton two-mass damper was installed between the 87th and 91st floors. This is essentially a mass spring damper system installed at the top of the building. 8 steel cables form a sling to support the large ball, while 8 viscous dampers work to absorb the energy that occurs when the sphere shifts. The two-mass damper can reduce the sway due to wind by up to 40%. The sphere can move up to 5 feet in any direction and is the world's largest and heaviest two-mass damper. We'll start our analysis of damping elements by looking at a mass damper system. The first thing I'd like to point out is that an ideal damper is represented by the following symbol. So now let's look at a free body diagram of our mass damper system. We'll have, in this case, the mass being acted upon by a damping force, labeled Fd. And I've drawn this to the right. This doesn't mean that the damping force is actually acting to the right. It just means this is the positive direction for the damping force. From the free body diagram, I can write the following equation of motion. Mx double dot equals F sub d. The damper opposes a change in its length. So let's suppose that the mass is moving to the right. That is, x dot is positive. Then the damping force would be to the left. That is, F sub d would be negative. Therefore, we can write the equation relating these two variables as Fd equals minus c times x dot, where c is the damping coefficient. You'll note the relationship between these variables is a linear one. Now given this, we can write the equation of motion. Mx double dot equals minus c times x dot. We'll now find the equation of motion for a mass damper system, but now with an input force added. And that input force is labeled F sub I, and I'll make the positive direction for it to the right. So the system is much the same as before, and we can now take advantage of what we learned. So we'll have mx double dot equals Fd plus Fi, and of course we know that Fd is minus c times x dot. And so then we can rearrange our equation of motion and write it in terms of the output variable x on the left-hand side and the input variable on the right-hand side. So that gives me mx double dot plus cx dot equals f sub I. From the differential equation, let's now find the transfer function. So we Laplace transform mx double dot plus cx dot equals f sub I, and we'll assume zero initial conditions since we're getting the transfer function. And what we find is as follows. X of s equals 1 over s times the quantity ms plus c times f sub I. So we have a second order transfer function between the input variable f sub I and the output variable x of s. The two poles of this transfer function are 0 and minus c over m. Clearly this transfer function is bounded input, bounded output unstable and marginally asymptotically stable. Let's now find the impulse response of this transfer function. So the transfer function is h of s equals 1 over m times 1 over s times s plus c over m. And then we can take this transfer function and we can partial fraction expand it. And we'll find it is 1 over c divided by s minus 1 over c divided by s plus c over m. We'll now go to our table and find the inverse Laplace transform of h of s, which is, of course, the impulse response, h of t. And that will be equal to 1 over c times the quantity 1 minus e to the minus c over m t times u of t. And this response is represented in the figure below. We see x of t is the sum of two terms. One is a step of magnitude 1 over c, and the other is a decreasing exponential. This is the impulse response of the system. It's what would happen to the mass if we were to hit it with a hammer. And what would it do? It would move a distance 1 over c. It would start to move, but then slow down and come to a stop. The energy would be dissipated by the damper. The initial velocity of the mass, immediately after we hit it with the hammer, would be 1 over m. And the time constant of the motion would be m over c. Now we know the response of any linear system to a step input is the integral of the response of the system to an impulse. And so we can easily find the response of this mass damper system to a step force that is applied to it. And the response looks like this graph. What we notice is the slope of the graph, in the end, is 1 over c. Of course, the slope of the graph of position versus time is the velocity. So this graph is indicating a terminal velocity for the mass of 1 over c. So we know the behavior of this mass damper system when the mass is acted upon by a constant force. After the transient dies down, the mass will move with constant velocity. So what does the curve of velocity versus time look like when a constant force is being applied to the mass? It will look like the response of the position of the mass to an impulse. So it's the same graph we saw before, except now the axis is changed. You should carefully look this material over to make sure you understand the relationships between the impulse response, the step response, and the motion and velocity of these mechanical systems. I'd like to close this lecture by giving you the rules for the equivalent damping of dampers in parallel and dampers in series. And the rules here are exactly the same as we found with springs. So for dampers in parallel, we simply have to add the two dampers coefficients together. The equivalent damping is C1 plus C2. For dampers in series, we find the equivalent damping by multiplying C1 by C2 and dividing by the sum of them.